So a graph you might come across in your studies around this is the shunt iso, or what's called the isoshunt diagram. And what this is, on the y-axis, you'll draw your PaO2 in millimeters of mercury, and on the x-axis, you'll draw FiO2. And what you can see here through these lines is that as the shunt increases, you need more and more FiO2 to overcome shunt to saturate the person. And once you get to 30% shunt, even at 100% FiO2, you can't overcome the shunt. You can't get the PaO2 above 100 millimeters of mercury. And once you're 50% shunt, you can't increase it at all. Generally, when you give someone oxygen, you times the FiO2 by 5, and that should be around what the PaO2 should be. You can demonstrate this in normal individuals because we know that atmospheric oxygen is around 21%, so FiO2 is 21%. And if you measure someone's arterial blood, you would see that their partial pressure of oxygen in their arteries would be around 100 millimeters of mercury. So you're probably wondering at this point, why doesn't giving extra FiO2 improve a shunt once it gets above 30%? Or in general, why it doesn't really help with the shunts, even at 10%. And it's to do with the fact that oxygen is carried in the blood in two ways, on hemoglobin or dissolved. And in the ventilated portions of the lungs with blood flow, once equilibrium is reached, essentially almost all the hemoglobin are saturated. You can't saturate more than 100% of the hemoglobin. So the only part of the blood left to carry oxygen is the dissolved portion. But oxygen's solubility in water and in the blood isn't very high. It's only 0.03 ml per litre. So the limiting factor here is how much oxygen you can dissolve in the blood. And this is represented by your oxygen hemoglobin dissociation curve, because once all your oxygen is saturated, you're in this flat portion of the curve. So every increase in partial pressure of oxygen, you don't get much gain in your oxygen carriage in the blood.